So I am Amy Sullivan. I am a research scientist at the Cooperative Institute for Research in the Environmental Sciences and also at the NOAA Earth Systems Research Laboratory. And my role in MOSAiC is that I'm responsible for coordinating the international forecasting efforts in support of the campaign, and then to use the forecasts during and after the campaign to understand the biases due to our lack of understanding of certain model processes that limit the skill of our forecasts. And so the talk today is on Arctic process modeling, where I'm going to be using examples from cloud processes in order to illustrate some of the concepts. So process modeling is an iterative process between observations and theory, where we start by making observations, and then we think of interesting questions based on the observations, and then we formulate hypotheses to explain the phenomena, and we develop ways to test these hypotheses, and from that, we develop new theories. And with that new understanding, we go back into the field and make more observations. And so this is an iterative process between the observations and the theory. So the story here that I'd like to tell starts with the surface heat budget of the Arctic Ocean Campaign, or SHEBA, which took place between September 1997 and September 1998. And it was a similar campaign to MOSAiC in that it was a drift experiment where an icebreaker was just drifting with the ice over a full annual cycle. And one of the observations that they made during SHEBA was that they observed liquid and clouds down to temperatures of minus 40 degrees Celsius. And that's what this figure shows here. So the x-axis shows temperature, and the y-axis shows the probability of occurrence. So the percentage of the time that these types of clouds were observed. And the solid line shows when there was only ice in the cloud. The dotted line shows when both ice and liquid was in the cloud. And the dashed line shows when only liquid was observed in the cloud. And what you can see is that the cold temperatures, say at temperatures less than minus 30, most of the time clouds were observed with only ice. But you can see that for a very large percentage of the time, both clouds were observed with both liquid and ice. At minus 30 degrees Celsius, you can see that over 40% of the time, clouds were observed with liquid. And liquid was observed in clouds down to temperatures of minus 40 degrees Celsius. And this was really unexpected. And the reason why it was so unexpected was because there's something called the Bergeron process, where at very cold temperatures, the atmosphere is subsaturated with respect to liquid, but supersaturated with respect to ice. That means the water vapor in the atmosphere will be deposited on the ice crystals before they're deposited on the droplets. And when the vapor is depleted by this process, that means that the droplets can't grow. And that means that the droplets will begin to evaporate. So because of this theory, it was really unexpected to find liquid in clouds at such cold temperatures. So I just want to step back a minute and explain why this is so important. This is a figure also from SHEBA that shows the cloud forcing when a cloud has liquid and when a cloud has only ice. So this upper figure is showing the cloud forcing due to long wave radiation. The middle figure is showing the cloud forcing due to short wave radiation. That's the radiation that comes in from the sun. And the lower figure shows the cloud forcing due to the combined long wave plus the short wave, so the total cloud forcing. And so these different lines, the solid line is for clear sky, so no clouds at all. The dashed line is for a cloud that has liquid, and the dashed dot line is for when a cloud does not have liquid, so it's only an ice cloud. So if you look at the upper figure, just focusing on the long wave radiation, you can see that the clouds without liquid have a distribution very similar to clear sky, except that we have these tails towards larger long wave cloud forcing. But what's really dramatic is that when a cloud has liquid, you see this very large shift towards positive long wave forcing. So this is to highlight that having liquid in clouds has a very large and dramatic impact on the surface energy balance and on the atmospheric structure. But what's really important is how well we're able to represent these processes in climate models, because there's something called Arctic amplification. That's when the Arctic is warming more rapidly than the rest of the globe. And that's something that we're observing today. So this is clearly a process that we need to be able to simulate in order to be able to make projections of future climate. And so what this figure is showing, the x-axis is showing the total Arctic warming, and the y-axis is showing the contribution from all of the different processes that contribute to Arctic warming. And this is for almost all of the climate models that were contributed to the last IPCC report. And so the slope of the line is showing that each of these models is representing these processes in a very different way. And what I want to focus on for this talk are the cloud feedbacks, which is shown in turquoise. And so if you look on the right, this shows the bar and whisker plots. And in the turquoise, you can see that the spread in the how these cloud feedbacks are represented in the different climate models differs by plus or minus 1 degree. And not only that, the different models don't agree on whether the clouds are playing a role in warming the Arctic or in cooling the Arctic. So this is showing that the uncertainties in how we're representing these processes are limiting our ability to make meaningful projections. So I've shown that it's really important to start with the observations and ask the interesting questions and developing, now we need to develop meaningful hypotheses. But what's really interesting is that most of the time, there are a number of hypotheses that can explain the same observed phenomena. And that's what's highlighted in this figure here. It's showing all of these are not all, but a number of different feedback loops that can contribute to the maintenance of liquid in clouds, which is represented by the box in the center of the diagram. And so this figure is highlighting 3 of the feedback loops that are known to play an important role in maintaining supercooled water. The orange one is showing that when we have, for example, a random updraft and liquid forms, that causes cloud top cooling through long wave radiation, which causes cloud-driven turbulence, which then causes, again, formation of the supercooled liquid. So this is a positive feedback loop. But what the blue feedback loop shows is that if you start with supercooled liquid, as I described previously, we have ice formation and we have water vapor being deposited on the ice before it's deposited on the liquid, which depletes the atmosphere of water vapor and prevents the liquid from forming. And so this is a negative feedback loop. And what this diagram shows is there's all these different feedback loops that play a role in the maintenance of the supercooled water in clouds. So we need to be able to design experiments to test these hypotheses. Which ones are more important? How do they interact? In order to understand what are the important processes that we need to be able to represent in these climate models. And so I want to use an example from the work that my team has been doing. And so what this is showing is observations that were taken with a radio sonde when there was a mixed phase stratocumulus cloud observed at about 1.1 kilometers high. And so what this figure is showing, the red is showing temperature, the black is showing potential temperature, which is a conserved quantity as dry parcels move up and down. And the blue is showing water vapor. And so if you focus on the red line, which is temperature, you see there's a kink at about 0.5 kilometers. And what this means is that the cloud layer is decoupled from what's happening near the surface. So if are sources of water vapor near the surface, this is showing that it's not going to be mixed effectively up into the cloud layer. And if you look a little higher at about 1.1 kilometers, you see that the temperature starts warming very quickly. That's called an inversion, which is very common when there's a stratocumulus cloud. But if you look at the water vapor, what's really interesting is at the same height as the inversion, we're also getting an increase in water vapor. And that's called a humidity inversion. And this is really interesting because this rarely occurs in the tropics. A lot of our understanding of stratocumulus clouds comes from studies done in the tropics. And so these humidity inversions at cloud top were very unexpected. But from recent studies, they occur quite frequently in the Arctic. And so one of the hypotheses that we developed is maybe in cases where a cloud is decoupled from the surface, maybe it's the water vapor at cloud top that can be the source of water vapor that maintains liquid in the cloud. So then we need to develop experiments to test this hypothesis. This is from a simulation of a cloud model where the horizontal resolution is about 50 meters, and we're writing out equations to describe the evolution of the clouds, the liquid in the clouds and ice in the clouds, and how that affects the atmospheric structure. So we've gone around this circle where we're starting with observations, and we're asking questions, and we're formulating hypotheses and developing experiments to test these hypotheses, and then developing new understanding. And with that new understanding, we go back into the field and make new observations. And that's where MOSAiC comes in, because even though it's a similar experiment to SHEBA, we have a lot more instruments to measure things that we were not able to measure before, and we have a lot of new understanding over the past 20 years that we are making measurements of and testing hypotheses with the new observations that we're making during MOSAiC.